Hello.
All right. It's like, it's 1 o'clock. Why not start? Hi, everybody. I hope you're doing well. I'm Nick, for those of you who don't know me. I'm one of the TAs in this Calc 3 section, actually for 2 Calc 3 sections. So I hope you're doing well. I hope you're staying safe, and thank you for coming. So I guess kind of what we're going to do here, since there's not a lot of people, I mean, a ton of people, honestly, what you can do, if you have any questions throughout this whole thing, you can just unmute yourself or just message me that you want to ask a question, and I'll ask you to mute yourself. If you want to ask me a question, just go ahead in the chat. Just say, I would like to ask a question or something like that. And then I'll call on you and you can unmute yourself. We can go from there. I'm going to share my screen a lot because I have a whiteboard that I'm going to be using too. And this whole entire thing is going to also be recorded also, just so you know, the people that aren't here, you know, can review it too, and also that the people that are here, you can go ahead and look back at some stuff. So I have all of those review materials I can pull up WebAssign. I can pull up basically anything that you have. I can just talk about different concepts and stuff, and we can go from there. So does anybody want to anybody have any questions that they want to start off with? I know that somebody did post on Piazza about a question that they wanted me to talk about, but is there any questions that you want me to talk about just in general? Any concepts, anything that you want me to just discuss, any problems you want me to do? I'd be happy to do anything like that. I can even go over past quizzes too. Let me know. So you can either, ask in the chat or just, unmute yourself and ask me a question. I'd be happy to answer it.
I have a question about the graphs.
Sure. What
So
kind
of so quiz 3 and then one of our review sheets that we had to do, we have to identify so they give us a graph and we have to identify which way is f of x or f sub x and which way is f sub y.
I know exactly which one you're talking about. Let me pull that up for you and let's share that together. Let's try to do that together. Yeah, that's a good question. Do you mean something like, I'm going to share my screen now, just so we're all aware. You mean something like this? With the level curves here, trying to find fx and fy, like that?
That's not the one I'm thinking of, but yeah, that's similar.
That's the idea though?
Yeah.
Okay.
Mm-hmm.
Oh, okay, so we can talk about this, and then if you want me to do another one, I'd be happy to. Okay, so what's actually happening here? Just to try to think about this. So what are the ideas of level curves, right? The idea of level curves here is if I basically take a surface, any surface that I have, I'm going to pick up some random things around my room, most likely. But if I take this, for instance, this is like a surface that I could describe, and what happens is a level curve, in this case, or a level surface, depending on how many dimensions we have, a level curve here, what we do is we say, okay, what curve describes all of the points that are at a specific height? So imagine you're on a mountain, right? Imagine I'm on a mountain and I slice off part of the mountain and I kind of draw what the intersection of that plane, that slice, and the mountain itself. I draw that intersection on the XY plane. And what we can see from this, and this is kind of the idea of a contour plot. What you're plotting there are all different contours, these level curves. So if you can see my mouse, kind of going from there, on this line specifically, x is 0, the function height is 0. That means we're at sea level, right? At this curve, this entire line, I'm always staying at a height of 1. So if you follow a contour line, you're always staying at the same height. That's also a really important thing going forward. So what do we mean by derivatives, and how can we use these graphs to kind of understand derivatives? Well, right, these topographical graphs are ways that we can see, if my function height's going up or down or changing height in different ways. And so the idea of derivatives, kind of going for this, is if I move, for instance, fx, right? What does this actually mean? This means if I move in the x direction, if I move in the positive x direction, am I going to be increasing my height, or am I going to be decreasing my height? Or am I going to be staying at the same height? And that's the idea of fx. So if fx is positive, that means as I go towards the right, I'm going to be increasing my height. If it's negative, it's going to be decreasing. And if it stays the same height, for instance, which means I follow a contour line, that means it's going to be 0. So for instance, let's take this point P, Q, and R. Let's try to understand the derivatives with respect to x and y. So if I take this point P, we see here that the function height at this point is somewhere between 2 and 3, right? We see that we have to assume on these contour lines and these contour plots that between those two graphs, they're always, it's literally increasing. That's what we kind of have to think about. So let's say it's around 2.5 for estimate here. So what we do is we say, okay, if I move to the positive x direction, if I take this height and I start to move in this direction, imagine you're on a mountain and start to move in this direction, we see here that I'm going from 2.5, I'm moving in the x direction, I'm going closer to the 3 contour rather than the 2 contour, which means that I am going from 2.5 to 3 rather than 2.5 to 2. So that means that my height is going from 2.5 and getting closer to 3, which means my height is increasing here. So my height is going to be increasing, which means in that case that the derivative needs to be positive, because that means my slope is increasing as I move towards my right-hand side. That's kind of the idea for that, at least for the x direction. Similarly for Q, now let's take Q. If I move in the x direction here, move in this x direction. We're at a height of 0 currently. If I move in the x direction, I hope you'd agree that we actually stay at 0. We stay at a function height of 0, which means my slope does not change whatsoever. And my slope doesn't change at all. And so what does that mean? Well, that means that as I move towards in the positive x direction, my height does not change. I stay on my contour line, and therefore fx here is going to be 0 because the derivative with respect to x is not changing. My slope is not changing there. And lastly here with r, again, I'm moving in the x direction here. Let's say I'm moving in the x direction. Well, if I'm moving in the x direction, I see that I'm somewhere between 0 and -2, but if I move in the x direction here, I'm getting closer to the -2. So I'm going downhill. I'm maybe around -1, for instance, but if I'm going closer to -2, I'm moving downwards. I'm moving in the negative direction. And so therefore, as I move in the x direction here, this means that my height is going to be decreasing, and therefore the derivative with respect to x is going to be negative. And that's kind of how you read these graphs in that way. So similarly, we could do this with the derivative with respect to y. The derivative with respect to y, what I'm going to be doing is I'm going to be moving in the positive y direction. So I'm moving in this direction. And we're going to see again if my height is increasing, decreasing, or staying the same. If I move in the positive y direction here, we see that we're getting closer again to the 3 contour rather than the 2 contour. So we can say then that my height is going from 2.5 to maybe around 3. And so therefore, for fy here, this is going to be positive. It's going to be a positive value. Similarly for q, if I go in the positive x direction, well, I'm at 0 and I'm moving towards 1, really, moving towards 1 here. So that means that I'm going to be moving in a positive direction, which means my slope is going to be increasing. I'm increasing my height, and therefore, this is going to be a positive value as well. And lastly, for r, we can say the same exact thing, because as I move in the positive y direction, I'm getting closer to 0. I'm at a negative height, so I'm actually increasing my height. So all of these right here should be positive, all for fy. And for fx, we gotta have positive, 0, and negative. That's kind of how you read these. And you can do this with really any direction. So for instance, if I took a direction, something like, -1, 1, right, and I move in this direction, maybe down in this direction, the directional derivative in that direction is actually going to be negative because I'm moving towards the 2 contour. Similarly, this one's going to be negative because I'm going to be moving down negative as well. So just by understanding the directional derivatives, I can tell you a direction, any direction, really. I can tell you the negative direction, like the -1, 1 direction. I can tell you, 45-degree angle in the bottom right hand. These are ways you can actually just visually see if it's going to be positive, negative, or 0. It's very tough to see, what the exact value is unless it's 0. So if I move tangent to my contour line, my derivative will be 0. That's a really important thing to remember. If I move tangent to a contour line and I'm on a contour line, if I move in it and tangent to it, just tangent to it, my directional derivative is going to be 0. That's really important to remember. And this will change drastically. Does that answer your question, Michaela?
Yeah, it does. So if we were given like a 3D plot though, it wasn't like the specific contour lines, and we have to describe like which one's f of x and which one's f of y. Is there a good technique to figure out which one's which?
Yeah, that's a good question. So I think you're kind of discussing almost, lab 5. I can kind of pull this up to kind of show, like something like this. I give you fx and fy.
Yeah, and you have to show which one's which, yeah.
Yeah. So we don't have the graph of f of x, xy up here, but what I would suggest doing is really the following. If I have any graph of f of xy, what I would suggest is, let me actually pull up a whiteboard here really quickly. Let me pull up that whiteboard. Can you guys see that whiteboard? Is that possible? Okay. So if you guys can see the whiteboard, please let me know if you can.
We can see it.
Great, thank you.
Yep.
Appreciate it. Zoom is sometimes weird. So if I have some function graph like f of x, y, something like, I don't know, something like this here, and I have, some function with respect to x or with respect to y. Maybe I can even do, you know what, let me actually do something better. I'm going to do a really, really simple graph. Something like this. Okay. So let's have, we have something like this. This is actually something like f of xy is equal to 1 minus x squared minus y squared. This is like a paraboloid, a down paraboloid. Now, if I tell you what the graph of fx and fy are, right, you can maybe even start to sketch it out. And now, how can you do that, right? How can you do that? Well, what I would suggest doing in some way is just take a point. Take any point that you want. Honestly, you could take, something like down here even. Okay, so what does this actually say? Some point on the graph here. Maybe this is the point. Maybe we can even consider this. Maybe this is the point. Actually, it's not going to be 2, 1. Whatever. Maybe I can just do 2, 1 here or something like that. That's fine. So let's even tackle the point 2, 1. I can even actually calculate fx and fy out, just to kind of show you something a little bit more. Fx here would be negative 2x. Fy here would be negative 2y. Right, kind of doing that out. Now, what does this actually say here? Fx at 2, 1 is going to be equal to negative 4. And f of y at 2, 1 is going to be equal to negative 2. So this means, and this is actually why I'm trying to get at this. This means that what I would suggest doing is take a point, for instance, 2, 1. If I move in the x direction, then I'm going to be moving at negative 4. That means on my graph of fx, there's going to be a point 2, 1, negative 4. And similarly here, on the graph of fy, at 2, 1, there's going to be a point 2, 1, negative 2. So if I go to my plot in fx and fy land, if I go my plot in fx, for instance, at 2, 1 here, my point should be at negative 4, basically, going down. Right? It should be negative there. Here. And because of this, this actually you can start to do something more like this, right? You could take a point, you can see maybe even if it's positive, maybe if I go in the x direction here, and maybe if I go in the x direction here, like just in the positive x direction, I can start to maybe see that the derivative is going to be decreasing faster than if I go in the positive y direction. That means at that point, it should be more negative than the other ones. So kind of thinking about this and thinking about that the point on fx is literally going to be the derivative at that point. In the same way that if I have some graph like fx here, and I wanted to plot the derivative, plotting the derivative, I know that at this point right here, I should be at 0. At this point here, I should be at 0 again. And then maybe from there, I see, okay, I have a positive slope here, so I should be kind of coming down like this, and then kind of maybe making something like that, in that case. It's the same exact idea. Maybe if you see that there's a kind of a very horizontal plane, if I go in the x direction, maybe I'm not increasing at all. Maybe if I go in the y direction, I'm increasing very rapidly. You should see that in the on the fy graph, it should be very positive. And on the fx graph at that same point, it should be very close to 0. These kind of tips will help you kind of understand that. Does that make more sense, Michaela, and everybody else?
Yeah, it does. Thank you.
Great, no problem. It's a tough thing to kind of, get at. There's not really a scientific way of going about it unless you know what the function is. You should kind of think about it though. If that's what I would usually do. I usually suggest that picking a point, going in the x direction, going in the y direction, and finding one that's very different, and then kind of mapping that over to fx and fy and going, okay, I found that this one's close to 0, this one's really negative. We could see at this point that that should happen. Sometimes it can be even more evident from that maybe y is very periodic in nature. And so fy is going to be very periodic in nature. Right? That's kind of, if you see like kind of a cosine curve, maybe in the y direction of f of xy, if you see that in fy, you should also see maybe like a sine, like the inverse of cosine there, right? I mean, the derivative of cosine. So like these things start to help out a lot. Yeah.
Sorry, this is like a really basic question, just sort of based off of this information. But if your fx, z component is negative 4, your fy z component is negative 2, then what would the z component itself be? Like of f of x comma y?
Oh, so we would just plug in up here in this function. We would just plug in f of 2 comma 1.
Okay, but then like how does that sort of compare to the fx and fy?
So what's great, and this is actually a really good point there. So the f of xy really has no relation to what fx and fy will be.
Okay.
It is only dependent on height. Because for instance, I know this sounds silly, but you know, regardless of if I'm gonna go off, if I am at the top of Mount Everest or I'm at the top of, you know, the Newark Reservoir, there's still a really big downhill. So it's just a matter of slope I'm thinking about. I'm just thinking about slope. In the same way that fx here, you know, f prime here does not really consider at all what the height of f of x is, right? It doesn't consider that at all. It just considers specifically the slope. And that's what you should think about the slope here specifically. That's kind of all it's kind of tackling.
Okay, perfect.
Yeah.
Thank you.
No problem. Okay. Any other questions here, at least on this stuff? What's it going to talk about? Okay. So I have a person asking about quiz 4B. So I'm going to go ahead and tackle that problem. Let me pull that up really quickly, if I have that. Do I have that actually? Hold on. What was 4B and 4C for you? A question. Who was that? I apologize. That asked me that question.
It was me. I asked it.
Yes, Camilla. Yes.
I can look it up and then get back to you.
You know, it's okay. I just want to make sure because I just what I want to do. Some students had different quizzes. Oh, it's quiz 4B. I actually can find that. Give me 1 second.
Okay.
Oh, so it was like find question 2. So find the gradient and the directional derivative, and then use the implicit function theorem, that kind of stuff.
Mm-hmm.
Okay. So I'm going to go back to my whiteboard. Okay. So let's move over a little bit here. Go ahead and do that. All right. So the next problem I'm going to talk about is, so this is from quiz 4B. And for those of you who had that, we're going to start with problem number 2, which gives me the following. So let's assume that I have a function f of xy, which is equal to x to the third y plus arctan of y. And my first question here is asking for what is the gradient at 1, 1. That's my goal. So let's at least first off talk about what the gradient actually means. So firstly, more specifically, the gradient tells us something very, very important. The gradient tells us that if I am at the bottom of a mountain, that's how I always like to describe it. If I'm at the bottom of my mountain and I do not care about my health at all, and I want to get to the top of the mountain as quickly as possible, which direction do I need to start to head in? And that will give me the direction of that is actually called the gradient. Now, how do we compute this? Right? The gradient here, we kind of denote this as an upside down triangle, the gradient of f. We're actually be seeing this notation actually a lot in the future, especially in chapter 16, with different stuff actually other than the gradient. But so the gradient here is equal to the derivative with respect to x and the derivative with respect to y. So what we want to do is calculate our functions, our multivariable function, we calculate with respect to x and with respect to y. So in order to do this, we tackle the fx here. The derivative with respect to x, I keep y constant, and I let I kind of just take it as I would with respect to x. The arctan is going to go away because it has nothing with respect to x. So here, if I do this, I'm going to take this derivative, which will just be 3x squared times y. And that's that one. And then with respect to y here, what I'm going to do is I see that, okay, well, both of these are with respect to y. This first one is kind of x to the third times y, so it's just going to be x to the third, because y is linear, so that goes away. And then the derivative of arctan, harkening back to Calc 1 derivatives, is 1 over 1 plus y squared. Kind of like that. And so now what I can do is if I plug in a point value at that point, it will tell me the exact direction I need to be heading in order for me to have my height increased. So if I plug in the point gradient of f at 1, 1, this is now equal to just 3. I think this will just be 3 here. Yeah, it'll just be 3 because 1 squared plus 1 case. And then over here, this will just be 1 plus 1 over 1 plus 1. And doing nice quick fractions, that first fraction is going to be a half. And so this will be 3, 3 halves. And now think about what this means physically, right? Physically, what this means is I'm at this direction right here. I'm at 1, 1. You can actually find the function height at that point if you would like to. Right? Arctan of 1 here specifically is, arctan of 1 is pi over 4, for instance. So you can actually find your function height pretty quickly, 1 plus pi over 4. And at that point, what it's saying is in a two-dimensional sense, if I go in the direction of 3 halves, so maybe something like in this direction here, it's a little bit more in the x rather than the y. What that says, if I go in that direction, if I just face myself and I face that direction, I start walking in that direction, my slope's going to be increasing the fastest. That's at least what that means in a gradient aspect there. And I can kind of prove that really quickly if you wanted to, but I'm not going to do that for right now because that's not really part of the problem. So that's how you calculate the gradient. And then similarly here in part B, we're asked to find here the directional derivative of f at the point 1, 0, in the direction of v is equal to 1, 1. Something like that. So if I'm able to do this now, trying to figure out how to calculate the directional derivative at 1, 0 and v in this direction, let's just remind ourselves of what the formula actually is. Let's remind ourselves. So the formula here, the directional derivative of f in the direction of u, because I'm kind of thinking about what's the slope going in that direction? How fast is my height decreasing, increasing, changing, just going in that direction u, is going to be just equal to the gradient of f taken with the dot product of u here. Now note the really important thing that u has to be a unit vector. If u is not a unit vector, if your direction is not a unit vector, you must make it by dividing out by the magnitude. Okay, so as we can see here, this v at the moment is not really a unit vector, right? The magnitude of v, if I calculate this out, is actually just equal to the square root of 2, right? Because 1 squared plus 1 squared. And so therefore, if I want to find my vector u to kind of make this work, what I would do is I would, oh, wrong way, sorry. So this would, this would actually just be 1, 1 divided by the square root of 2. And that is now my unit vector. It's still staying in the same direction, right? It's still that 45-degree angle going upwards in that direction, but now it's scaled back and I can actually utilize it. And the reason why we need that to be a unit vector, right? Why do we need it to be a unit vector? Is because what's actually happening here is we're almost taking a weight of like a W-E-I-G-H-T. We're taking a weight of both going in the x direction here and in the y direction. We're kind of thinking like, okay, I'm going fx this much, I'm going fy this much. So I'm kind of taking like maybe half and half. In this case, I'm kind of almost taking half and half. I'm taking a little bit of x and a little bit of y. If I'm just going in a different direction, maybe I'm taking a lot more of the x derivative and a little bit more of the y derivative. It's kind of nice how it works out that way. And so here what I'm going to do is now I'm going to use this u vector. The next thing I need to do is calculate the gradient of f at the point 1, 0. The gradient of f at 1, 0 here, just plugging back into my gradient formula up here, this still works pretty well. This first component is going to be actually 0, right? That first, because it's a 3x squared y. And then similarly over here, this derivative is just going to be 1 plus 1, right? 1 plus 1. It's going to be 0, 2. And so therefore, if I want to calculate the directional derivative at the point 1, 0, going in the direction of u, it is just coming out to be 0, 2, taking with the dot product of 1, 1 divided by the square root of 2. And the dot product here, again, is going to come out to be a number. Your directional derivative always is a number. You should never have this as a vector. You should never have it as a vector. And so here, what I'm going to do is that x component is not going to matter, and I'm only going to get that y component. So it's just going to be 2 divided by the square root of 2. And this right here is my answer for the directional derivative. And what is this actually saying? This is actually saying that if I'm at the point 1, 0, and I move in the direction 1, 1, if I just move in that direction, my height is going to be increasing at a rate of 2 over the square root of 2. which actually I think just comes to be the square root of 2. Yeah, this comes up to be the square root of 2 because I just
question about that.
Yes.
So when you say like a rate of 2 over the square root of 2, like, can you quantify like the I guess like the dimensions of the units that rate would be? Like, is it 1 unit of z for every 1 unit of x that rate would be in, or like, how can we think about that in terms of like the geometric space?
Yeah, that's a really good question. So it is a rate. So the basic idea is if I go, so the first, I guess, let me be kind of careful here how I say this. In the idea of the rate there, we have purposely made this vector that we're going in a dimension of 1, right? A unit of 1, right? A unit vector,
yeah.
right? We've made this unit vector, which is really important because why did we do that? Well, this really says that if I go in this direction 1 unit, if I go in that full direction, the slope of my tangent line means I kind of, what I'm doing here, right? This is also the slope of the tangent line in the direction of u. Right, so it's saying if I go 1 unit, which is this full unit of this vector, I'm going to be increasing my height by 2 over the square root of 2.
Gotcha, that makes sense, thanks.
Yeah, and fx in that case, as you said, that means that if I move 1 in the x direction, I'm moving, so much in the z direction. There. And it's the same exact way for here. Yeah. It's a very good question, though. It's a really important one. And yeah. So that's kind of what we do. That's why we have to kind of scale it back in some way, because we need the rate to kind of make sense in some way, right? We need that rate to make sense and kind of, kind of try to figure out how to quantify everything and kind of compare everything.
I have another question off of that. So would we ever be given the unit vector, or we like always have a vector that's not a unit vector and then have to translate it into one?
It really depends.
Yeah. Okay.
It really depends. Honestly, whatever the professors want. Most of the time in the real world, you're not really. I mean, most of the time you're not going to have a unit vector, so you kind of just have to scale it back down. A couple ways to make unit vectors. I know this sounds silly, but there are different ways to make unit vectors other than this. Because, for instance, if I told you, for instance, I want to just go in the. Ooh, my pen did not start working. So if I want to go, for instance, if I say I want to move in the theta equals pi over 4 direction, you might think, like, okay, how do I think about that? Okay, I need a unit vector. How do I do that? Well, you want to think about it. If I'm moving in a certain direction, pi over 4 is honestly just, in the 45-degree angle land. And so how do I come up with that? Well, if I give you a theta equals pi over 4, what I can then say is, well, I know that I can kind of form the triangle based off of it, right? And I know that this part is going to be based off the cosine, and this part's going to be based off the sine. And so if I do this, I can make my unit vector pretty nicely by just doing the cosine of theta and the sine of theta here. And so this would be, for instance, cosine of pi over 4 and sine of pi over 4 are the same thing. So this would be, square root of 2 over 2 and the square root of 2 over 2. And so this is another way you can make the unit vector. Always, and honestly, you should never assume that it's a unit vector. If they give you a vector, just if it says you should never assume that it's a unit vector. It says you. Some people use you just to kind of screw you over. Sometimes, it really depends. So make sure always your first thing, especially if you're doing a directional derivative, just go, okay, we're gonna do a sanity check. I think it's a unit vector. Just make sure it's a unit vector and go from there. Yeah.
Great, thank you.
No problem. Any other questions on this kind of aspect here? Okay. I know there's also a call to kind of go over the implicit function theorem. That concept is also on this quiz. So I'm just going to continue going with that here. And I'm going to keep moving over my whiteboard. Yes. And by the way, again, I'm going to have this whiteboard this whiteboard is going to stay. It'll stay up on Piazza, and you can just go look back at it. I'm not going to erase anything if you have any questions about it. So again, what we're going to talk about now is the implicit function theorem and kind of what this whole thing means. So I don't want to use. I'm not going to use that. I'm going to use function theorem. And so the implicit function theorem here tells me actually something really, really important. It's actually an application of the chain rule here. And I just want to kind of at least talk about why we have it and kind of, the importance of it really, really briefly, and kind of how we get to it. So if I have a function, this actually comes from this. If I have a function of f of x, y, and z that's equal to 0, I have something like this. And I tell you that, z is a function of x and y. Right? I tell you that z is a function of x and y. And my goal here is to maybe figure out, okay, how fast does z change with respect to x? All right, that's my goal. So let's kind of, think about this, briefly here of kind of what we would do. And what we would do here is we would kind of use the chain rule, right? We would kind of use the chain rule. And why is that? Well, I know that f, let's kind of think about this. I know that f is a function of 3 variables, x, y, and z. I know f is a function of x, y, and z. As well, I do know that x is itself a function of x. This sounds really silly, but x is a function of x. It's x, but it's a function of x. Y is not a function of anything. And z is itself is a function of x, right? Because of this here. So what I could do instead is kind of use the chain rule by taking the derivative of both sides here of this function with respect to x. The derivative of 0 is 0, so the entire thing stays. And this also works if this is just a k. If this is just a constant, this also works too. But the important thing here is everything has to be to one side. If you don't have everything to one side, you need to get it there. So in this case, what I'm going to do is I'm going to use the chain rule. As a reminder, I have my x with respect to x. I kind of think about this as a tree. I have the derivative of f with respect to x multiplied by dx dx. We'll talk about what that means in 2 seconds. Then y doesn't have any functions of x, so I just kind of leave it. Doesn't really matter in this case. But I know that z is a function of x, and f itself is a function of z. So I'm going to take df dz times dz dx. And now I want you to note here very quickly why I'm using these different notations, just to kind of make sure. If I ever use this partial notation here, this kind of partial notation, that means that that function on top is dependent on more than one variable. If I just use the straight d here, kind of like that, that means specifically that that function is only dependent on one variable. Okay, so if I have multiple variables, I must use the partial notation. That's why over here, I have to use that, because z is dependent on both x and y here. I should also say z is dependent on x and y. And y is also dependent on y. Something like that. So this is going to be equal to 0. And why is that? Because the derivative of a constant is also 0. So that goes away. Dx dx, well, what's the derivative of x with respect to x? Just 1. So this becomes df dx plus df dz times dz dx is equal to 0. And now what I'm going to do is I'm going to solve for dz dx, right? I solve for dz dx by subtracting over df dx. I'm going to get df dx. I'm going to subtract that over, and then I get, df dz on the bottom, just by dividing that out. I can maybe write this more succinctly as this negative f sub x over f sub z. And this right here is the implicit function theorem. So what does this say? This says that I don't have to go through that horrendous, like, Calc 1-esque, taking implicit functions and making sure I use the chain rule in that way. I don't have to do that anymore. I can kind of just almost do it blindly, which is kind of nice. I don't have to kind of worry about my chain rule things. The chain rule's already been implemented here. So what does this really say? If I have a function of z and it's with respect to x, this works for anything. This works for if it's y with respect to x. This works for z with respect to y. Anything like that. I just take the derivative of my function up here, the function up here, which is equal to a constant. I take that function, and I take the derivative of this with respect to x, just with respect to x, and then take it with respect to z, just with respect to z. I don't assume anything else. It's just the partial derivative. Just divide them, and making sure we include this minus sign. So in our case, for this problem, just kind of going over this, oh, whoopsies. We're now going to move this guy over. So if I now have the problem here of y sine of z minus x squared is equal to 4xy, something like that. And I would like to find, let's assume I want to find a dz dy. Okay. What I need to do first off in this process is to use the implicit function theorem. I need to move everything to one side. This is necessary. This is absolutely necessary to do it. If you do not do it, you cannot use the implicit function theorem. Move everything to one side. Don't even move the constants. Why not? Right? You can do that. So moving everything to one side is probably going to be a little bit easier to move over the 4xy. So I'm going to get y sine of z minus x squared minus 4xy is equal to 0. I'm now going to define this function right here as my function of x, y, and z. Okay, if I want to find dz dy, I'm going to now take the partial derivative of this function with respect to y, divided by the partial derivative with respect to z. The function that is dependent on two other variables is always on the bottom. Right? The function that's dependent, right? You kind of flip these. If you see it's dz dy, it's going to be fy, fx. These should be flipped. It should be reciprocals in some way. That's a bad use of reciprocals, but please bear with me on that. Taking this derivative with respect to y, we see that I'm only going to have a sine of z on the top, minus the x squared is going to go away, and then I'm going to have negative 4x there, kind of like that, divided by the derivative with respect to z here. The derivative with respect to z here is just y cosine of z. That's really it. It's really simple, which is nice. The calculation is very quick because it's just partial derivatives. I don't have to worry about chain rule in that case too. You can leave it as that. You can also just flip it if you would like. There's not really a convention here. It really depends on what you're going to be doing with it later. But it's kind of your answer, and you can leave it like this, right? This is as simplified as I want it to be, and this works for fx, fx, fz. This works for anything like that. The main concern, and you want to really know about the two things: the minus sign out in front is necessary, as well. The partial derivative with respect to the the z goes on the bottom and the y goes on the top. It kind of flips in that way. In that case, and making sure you have everything to one side. It's really important too. Okay, does anybody have any questions about that? Is the implicit function theorem here or anything about it? Okay, so what are the questions you guys have? I'll take any other questions now.
Can we go over on the mini exam, like the practice one, question 6b?
Yes, we can go over that. Sure, give me 1 second. I think also, Jack, I will come to you next.
Well,
Okay,
thank you.
You gotcha. Nikki, what was that again? Which one specifically are you talking about?
The mini exam, like the practice one.
It's a chain rule question, I'm pretty sure.
Is it this one? Like this PDF?
No, I think it's a different one.
Got it. My bad.
It says mini exam 1 at the top.
Okay. Not this one either, right?
It's that.
Oh, it is this one. Okay.
So
Great.
6b.
6b. Ah, this guy.
Mm-hmm.
Here. Okay. Let me write this down. It's a little bit of a longer one here. So what are we actually doing? We are doing here, I have an equation, the natural log of cosine of z plus tangent of xyz is equal to x squared, where z is a function of x and y. And I have that x here is equal to 8u squared plus 3v. And I have that y is equal to the square root of u divided by v. Okay, great. So All right, that's our problem here. I have this. I have the natural log of cosine of z plus tangent of xyz is equal to x squared. And then I have z is equal to f of xyz. And my goal is to find dz du and dz dx, dv. So let's think about what the chain rule is again, kind of thinking about this here. So in this case, it is going to be very important here to remember that what is the basic concept of the chain rule specifically. So here, I see that z. Hold on one second. Here. So z itself is a function of both x and y. Here. As well, x here is a function of u and v, and y is also a function of u and v. Now, if I have, in this case, let me actually see something very quickly. Hold on one second. I'm sorry about this. Give me a second.
Could we expect to see like this length of a problem on an exam where we have to do chain rule but also use implicit function theorem to find like, derivatives?
Yeah, that's yeah. So
seems kind of long.
It would be a very long problem. Yeah, because you have to do a lot of different things here, right? It is kind of a combination problem. So the thing that's a little bit interesting, yeah, this is a really long problem, but you know, if I come up with a little bit of a simpler question, I could go about it relatively quickly. So I guess the basic thing here is to remember, we also have the fact that f, you know, here, we know we can get, for instance, dz dx out of this by, you know, doing something like we did in the implicit function theorem, like negative fx over fy as well. And we also have, you know, that dz dy here could also be written, I'm sorry, dz df dz on the bottom here. And we also have that this is fy over fz here. Right, we also have this. So you have to kind of take this into consideration when you're kind of going about it. I think, yeah, so you do have to take this into consideration. As a reminder, let's kind of think about what this actually means, right? If I have this, if I just have this schematic here, even if we don't have this really complicated of a problem, right? If we don't even have this complicated of a problem, we have this guy. If I wanted to find dz du, how do I write this out, right? I know that dz du, well, I know that x is a function of u and that z is a function of x. So I can write this out where I have dz dx and then I have dx du. Oh, du. Yeah. Right? I always want to make sure that if I kind of do horrible cancellation here, dx is kind of cancel. I should kind of look like dz du. As well, I know that dz, you know, dy du, I'm going to have that because y is a function of u, as well as z is a function of y too. So this is going to be as well, that this will be dz dy, I have to go down this branch, times dy du. Now, the issue comes from the fact, and it's really interesting here, the issue comes from, you know, dx du and dy du are not hard to calculate, right? Those are not hard to calculate really at all. Right? It's just the derivative of x with respect to u, it's the derivative of y with respect to u here. Right? It's not too bad. But the big thing is going to come into play where I do still have to calculate dz dx and dz dy. And how am I actually going to calculate those, right? How am I going to calculate those? Well, I'm going to calculate these guys more specifically, I have to utilize my implicit function theorem. There's no other way, because to get those originally, I would have to have a function z equals something. But I have up here that this is dz dx and dz dy. I can kind of utilize my implicit function theorem to kind of get this. It's kind of like a multi-step part here. You really need multi-steps, because in order to get dz dx and dz dy, you need to utilize another facet of the implicit function theorem here. Or if you didn't want to use the implicit function theorem, you could actually make a whole schematic, just of specifically with respect to f and all that, but it's going to get really complicated there too. So in order to do this, I'm going to need to calculate dz dx and dz dy here. So the first thing I'm going to do is I'm going to move over everything onto one side, as we did in the last problem, which will be the natural log of cosine of z plus the tangent of xyz minus x squared equals 0. If this problem does show up, wow. I mean, this is a really good problem to kind of think about, but it's a really, there's a lot of really interesting facets to it. Really, really interesting. So I'm going to name this fx, f of xyz. And now to calculate dz dx, I'm going to take the derivative with respect to x. I'm going to take the derivative with respect to z here and kind of divide them. So the derivative with respect to x here, kind of going through this first part, the natural log of cosine of z is unnecessary. I don't really have to tackle that. Kind of goes away. So then the tangent of xyz, the derivative of tangent is secant squared. And so I would have a secant squared out, and then I'll have to pop out using the chain rule, the derivative of this inside here. The chain rule here with respect to x would be yz. So it'll be yz times secant squared of xyz. Kind of like that. And then I would get this minus 2x here on top of it. And then similarly, dividing by z here, well, it's going to be a little bit more complicated. But the derivative of the natural log of cosine of z is 1 over cosine of z multiplied by negative sine of z. Right? It's actually multiplied by the derivative of cosine of z. So that actually is going to be sine of z over cosine thing. I think that comes out to negative tangent of z. Kind of doing that out just as a kind of a thing, right? So it'll be 1 over cosine of z multiplied by negative sine of z. So this comes out to, tangent of z, negative tangent of z. And then similarly here, we would have again that this would be a plus, xy secant squared of xyz. And so this right here is dz dx. This very, very long formula here. In a similar way, we can do y, where this would be negative xz secant squared of xyz. And we divide it again by the same exact thing that we had up on top. And now, kind of coming back and kind of thinking about what we're doing in the whole concept of the problem, our goal was to find how does z change with respect to u, right? I can write this formula down, right? This chain rule down pretty quickly here, right? I can do this pretty quickly just by using my kind of tree that I'm using. From there, I need to then figure out how to calculate dz dx and dz dy. The ways to do that, usually, if I have a function of z is equal to f, if I have z equals f of xy, something like that, it's not too bad, right? I just take the derivative with respect to x, derivative with respect to y. Here, though, I don't have that, right? I actually have specifically that, I need to calculate this a different way. And the way to calculate dz dx, also in this case, because z is implicitly defined here, is to use the implicit function theorem. So what I'm going to do then is I can calculate dx du. Dx du here. Dx du is actually pretty quick because it's just this derivative up here with respect to u, which is just 16u. And dy du is also not too bad. It's just the 1 over the 2v squared of u. We do that right by, this is just, u to the 1/2. I move that down. And so using these two things, we can plug these guys in and get our full final formula. I'm not going to go ahead and write all that out. I think it's a little bit too tedious at the moment. But again, what we would do then is we would take, this guy up here, dz dy, dz dx and dz dy, right? Take this guy over here too, and put them into our formulas, and multiply it by 16u and 1 over 2 times v times the square root of u. And similarly here, if I wanted to do dz dv, I could do the same exact thing, where I would still need dz dx and dx dv this time, and then I would dz dy and dy dv here, just by utilizing the chain rule. The big thing you should realize, at least, is to use these chain rules here. Using the implicit function theorem on top of it, that's a really interesting question and a really cool way of thinking about it, and actually a very valid way to come up with it. But it's not absolutely necessary that you definitely know the concepts and see that you can get it from the implicit function theorem if you need to, your functions. But yeah, it's kind of how I'll go about it. Does that answer your question?
Yeah, thanks. That was really helpful.
Yeah, cool. It's an interesting problem. That's actually a really I'm gonna keep that in my back if I ever teach an honors course. I think that's a really good question. All right. Any other questions on this specifically? This guy? Okay, I did. Jack, right? You had a question?
Yeah, I just I wanted to go over like the whole end of 14.6 because like I'm very cool with like using the gradient as the normal vector for the tangent plane or the slope vector for the normal line, but I'm still not entirely sure of like what the geometric interpretation truly means. Like I know how to do the problems, but I feel like I would be better suited to take an exam if I actually 100% knew like what spatially was going on.
Yeah. The difference between like a 2D and a 3D gradient is actually very subtle. It actually means the same thing. So let me at least tackle that. Yeah, that's a good thing to kind of tackle here. So kind of just as a briefing before we kind of get into kind of the geometric interpretation, right? We have this idea of the gradient. Again, the gradient can be calculated as fx, fy. If I have a third component, it could be fc, or something like that. And we can find, if I do this, that if I want to create a tangent plane, if I have something like, if I have a function, as you can see, I write this a lot, fx, y, z is equal to k. If I have something like this, and I want to find a tangent plane to a point, let's say x0, y0, z0, something like that. What I can find is if I want to find my normal vector actually is equal to, of the plane, of the tangent plane, is actually equal to the gradient at my point. Now, why is that? Right? Why is this the case? Now, geometrically, what is this actually saying when I take the gradient here of a three-dimensional object? So I want to just, let me do a very basic example of something that we can definitely see and kind of go from there. If I have a function, x squared plus y squared plus z squared. So let's take this guy. X squared plus y squared plus z squared is equal to 1. Okay, if I have x squared plus y squared plus z squared is equal to 1, I hope we all agree that that's a sphere of radius 1, centered at the origin. Yeah? So something like my little ball here that I have. Something like this. Now, I hope you'd agree that the normal vector here of this ball, anywhere here is always pointing outwards of the ball, right? Kind of what that means. So let's just calculate really quickly this thing and kind of see what I mean by this. Well, what do I mean by the gradient here, right? That's kind of what we're thinking about. So I have something that of this form, f of x, y, z is equal to k. So I'm going to name this function, I'm going to name this function g for the time being, just so we can kind of see something. This is my function g of x, y, z. So is equal to x squared plus y squared plus z squared. Okay. Now, if I take the gradient again, right, if I just take the gradient of this, the geometric interpretation of the gradient, as we can prove actually pretty nicely, right? We know for a fact this means, by just mathematics, it means the direction of fastest increase, right? If I go in that direction, I'm going to be increasing the fastest. And that's kind of nice in two-dimensional sense, like in a two-dimensional gradient sense. What does that mean in three-dimensional gradient sense, right? So if I calculate the gradient here, I think it's pretty quick to see that the gradient here is with fx, fy, and fz is just 2x 2y, and 2z. Now, what does that really mean? Right, what does that actually see? Well, if I take 2x, 2y, 2z, which could be written as 2 times x, y, z, if I want to factor that out, what is x, y, z really saying? X, y, z, if I pick a point, right? If I pick a point, right? I'm not going to even kind of do this. Well, what is this vector? What does x, y mean? Well, the vector x, y, so if I pick a point x, y, the vector is just in that direction, right? It's just the vector in that direction here, going in that direction. So that means it's just pointing outwards, away from the origin, right? This vector, this normal vector, is pointing directly away from the origin. Now, why does that make sense that that's the gradient? Right? Why does that actually physically make sense that this means that's the gradient? Well, imagine if I had like Russian nesting dolls. But in this case, I just had spheres. Imagine I had another sphere on top of it, and another sphere on top of it, and another sphere on top of it, with bigger and bigger radii, that kind of concentric spheres. I hope you'd agree that the direction here that I would be pointing in this way would actually be the direction towards the next largest sphere encompassing it. Okay? It's actually the next largest sphere encompassing it. So what is that actually saying? That's saying that if I want to get to the next largest sphere, imagine I had another sphere. Imagine if I had a sphere of radius 2, x squared plus y squared plus z squared equal to 4, right? It would actually be that this direction, the direction x, y, z, would get me to that surface the fastest. And what is it actually saying, right? In the same exact way, in a two-dimensional sense, if I have here, if I just had two-dimensional sense, a gradient here, I mean, this is maybe a contour plot, right? This is a contour plot of all this. And I'm a point here. And I want to find, the fastest rate of change, right? The direction of the gradient. I know the gradient is always orthogonal to my contour lines. That's my goal, right? We can find that it's actually orthogonal to my contour lines. Maybe something like that. It's exactly orthogonal. In the same exact way, that gets me to the next contour line. Right? Imagine I have something like this. That gets me closer to the next contour line. So that gets me to the next level curve. In this case, the gradient here gets me to the next level surface because it's a three-dimensional object. So in this case, this is really saying g of x, y, z is equal to 1. This gradient right here gets me closer to, for instance, g of x, y, z is equal to 4, which is the level surface. It's all the values of x, y, z now that are equal to 4. In this case, all the points, 2 units away from the origin. So because this orthogonality thing holds both in 2 dimensions and 3 dimensions, it is just basically saying, I'm trying to get to the next level surface in this case, rather than next level curve. And that kind of aspect there, that kind of understanding of the fact that, you have this normal vector, right? This orthogonality condition, both in 2 dimensions and 3 dimensions. And this orthogonality condition in the 3-dimensional case here actually physically means, right? Actually physically means that I'm going to my next level surface, which is also orthogonal to my current level surface. And so that's why, in a nutshell, the gradient of f is actually the normal vector to my surface, and specifically the direction of the normal line in that case too. There's a little bit more math behind it. I can kind of go there if you would like. But I hope that visually, geometrically makes more sense there. I like to think about it, at least in the most basic sense, like the concentric, the sphere sense. It's kind of going towards, bigger and bigger and bigger spheres. It's going outwards, right? That's this XYZ thing is actually going directly away from the origin. And that kind of gets me, specifically, think about the direction to the next level surface there. Does that answer your question?
I have a quick question about that.
Please, yes.
So what's the difference between a level surface and a level curve then?
So a level surface is a 3-dimensional function like g of x, y, z, which is equal to a constant. And a level curve is just a function of x and y equal to a constant.
Okay, thank you.
Yeah, so one's just a function of 2 variables, one's a function of 3 variables. Yeah. Does anybody else have any questions about that? I hope that cleared things up a little bit. It's a weird kind of concept there. It is a little bit tough. But that's kind of the general gist, is that you should think about the gradient regardless as a normal vector. The gradient is always a normal vector, regardless if it's 2 dimensions, 3 dimensions. It is normal always to the level blank, the level of curves, level surfaces. You can even do higher dimensional stuff too. And that can get you some really interesting things, especially if I want to find, how fast will I need to move X, Y, and Z to get to my next height? Because you can think about G of X, Y, Z maybe as a function of 3 variables, that where X, Y, and Z are all things that you have just in general, right? I mean, maybe it's like temperature and pressure and density and this stuff. And kind of combining all of them can tell you how I need to move the density, the temperature, and all these different variables, to get to my next height, to get to this function value to be something else in that case. And we know for a fact geometrically that's going to be orthogonal. You can also find too that if I have, this is just a really a little more higher thinking here, but we don't have to kind of go through this. If I have any like a surface here, and I take any line on it, I can call this R of t here. R of t, any line on my surface. And this function can be thought of as f of x, y, z is equal to 0. We can actually find, using the chain rule, pretty cool, you can find that the chain rule here can actually admit that the gradient of f with the dot product of r prime of t has to be equal to 0. And so what does that actually mean? That means that the derivative, the direction that this curve is going on, which is staying on my surface, is orthogonal to my gradient. Right? It's orthogonal to the gradient, so the gradient has to be pointing in this direction. And so kind of thinking about this orthogonality condition, is orthogonal to any tangent line, any tangent curve you draw on your surface at all. It always has to be orthogonal. And this actually stems very, very quickly, surprisingly, using this definition of the chain rule. And kind of noting that is kind of also more on the lines of thinking about, how do I kind of visualize the chain, even the chain rule? Like, how do I visualize the chain rule? How do I visualize what a normal vector is, and how do I normalize kind of think about what a gradient is? Yeah, I hope that answered your question, Jack. If that makes sense.
Yeah, that makes a lot more sense with the whole equals k thing. Thank you.
Cool. Yeah, no problem. This stuff is really, really, you can get really deep in here. I promise you. You're really cool in the weeds. Okay, what other questions can I answer? What other questions can I kind of talk about here? Anybody can kind of chime in if they want.
Could we actually do a limit problem, maybe like 2B on the mini exam?
Yeah, is it the one that DJ posted? That one?
Maybe it's x squared plus y squared with e to the square root. I think he might have. Yeah,
he messed it. So it's 1 over that. Well, e to the 1 over.
Oh, okay.
Yeah, but we can still do that one.
Because don't you have to basically turn it into like terms of r theta and put it into polar form?
Yeah, you do. We can kind of go over that if you would like, regardless.
Yeah.
We can like talk about that. Sure. Sure, we can talk about that. So this is from the mini exam here. That DJ posted.
2B.
Yeah.
Mm-hmm.
Yeah. Okay. So let me at least. Trying to find out what's the best place to kind of write this here. Okay. I'm going to come back then and move over here now. All right. So we're going to tackle this question. So it's the limit as xy approaches 0, 0 of x squared plus y squared e to the 1 over x squared plus y squared. This guy here. So this problem, I mean, just in general, how do I come up with these kinds of problems? How do I start to even think about how to compute these? So the first thing that you always want to do is, if I ever note that I have like an x squared plus y squared, you want to immediately, you think about that. If I have x squared plus y squared or something like that, and you don't see like a really nice way, at least really quickly, maybe there's a really nice quick way to maybe go about it, maybe like x equals 0, y equals 0, something like that. But I don't have that off the bat, right? the first thing you might want to suggest doing is maybe try to go to polar. Now, polar coordinates don't always admit good things. You know, don't admit some nice properties here. But regardless, what we can at least think about doing is it's a great way to think about it, because what is the idea of polar coordinate limits, right? What is the idea of polar coordinate limits? Just at least a visual aspect of it. If I have something like XY here, and I give you a direction theta, right? I give you a direction theta. Maybe it's this direction here. And what do I mean by a direction of theta? It's this direction here, this direction of theta. It could also be something like this, right? Kind of coming into this angle. This could also be another theta. This tells me this is a way to prove that all lines go to the same exact point. If I show this for all theta, this means that regardless of which line I go in, it will always be the same limit, which most of the time for our cases will work. In this case, there are some very, very interesting cases where it doesn't really make sense to kind of do this. You need to satisfy some really, really interesting conditions. But for most of the cases here, we can at least say that if we show that the polar limit goes to something, we can find that the entire limit can go to it. For at least our cases too. You need continuity things to hold and stuff. We can at least work with it. So if I see this x squared plus y squared here, at least think about why this would help you. If I change this x squared plus y squared here, you know, to r squared, the goal always of limits is to convert this to a one-dimensional limit, if you can. If you can convert this to a one-dimensional limit, we have all these properties. So why not do it? And so what I'm going to be doing here is, again, this is as r approaches 0 from the right-hand side. This is really important because radii can't be negative, right? So we're assuming that the radius will approach from the right-hand side of 0, and this has to hold for all theta. So exchanging this here, we can at least write this that the limit as r approaches 0 here, which is the origin. R approaches 0 from the which is going to be the origin, from the positive direction. You always need that. The right-hand side, if you will. Now I replace this as r squared, and this is e to the 1 over r squared here. Something like that. Converting this limit now gets me off the bat, you know, at least something nicer, right? This is at least something that I can actually start to compute and maybe use some techniques on. So now how would I go about computing this limit? Because now this doesn't have any theta in it, so I don't have to really worry about theta at all, which is really nice, which is actually really, really nice too. There's no theta in it. I don't have to keep that around. I don't have to think about that. How do I go about this? Well, if I plug in 0 just off the bat, I'm going to get a 0, and I'm going to get an e to the 1 over 0, so it's going to kind of be infinity here. So if I have a 0 times infinity thing, usually that denotes me to kind of go to L'Hopital's rule. So L'Hopital's rule, again, means that if I have a function divided by a function, and the limit has something like 0 over 0 or something like that, right, what I could do is I could take derivatives of the top and the bottom and work from there. So what I could do instead is I could rewrite this. Well, I'm going to leave the 1 over e to the 1 over r squared, and move the r squared to the bottom to make it 1 over r squared. Something like this. Okay, so something like this. And now I can utilize L'Hopital's rule with respect to r. So if I use L'Hopital's rule, kind of going through this, I take the derivative of the top and I leave it at the top. So the derivative of the top here is going to be, you know, using kind of exponential rules. The derivative of 1 over r squared is -2 over r to the third. So this limit as r approaches 0 from the right, which is going to be -1 over r, -2 over r to the third, e to the 1 over r squared, divided by, and again, over here, this is going to be 1 over r squared. So this is, again, going to be pretty nice here. Oh, it's actually equal to the square root of, oh, it's square root. I'm sorry. This guy was a square root. My apologies. This exponent up here was actually square root in the problem. Sorry. So this should just be an r then. Here. I was wondering, I was like, oh, this is going to be weird. It's a 1 over r. It's going to cancel. Sorry about that. So this is going to be then the derivative of 1 over r is going to be -1 over r squared. And now on the bottom here, this derivative of 1 over r squared is going to be negative 2 over r to the third, as I had wanted to say before, unfortunately. So what I'm going to do here is kind of cancel some things. We can find then that if I do this out, you know, the r to the third can come to the top. It's going to kind of cancel out. So it should be something like, you know, so the limit as r approaches 0 here on the right. I'm going to have this 1/2. I'm also going to have here an r to the third over r squared e to the 1 over r. Squared here. And this guy is going to just be an r. So the limit as r approaches 0 from the right of 1/2 r e to the 1 over r. And I'm back to the same issue that I had. I go to 0 again, and I can't do it again either, right? I can't do this again here. So I have to use L'Hopital's rule a second time, or as I continue to call it, a little hospital, but we don't have to go from that. So I again have the limit here as r goes to 0 from the positive side. I'm going to move this down again, as I would. I'm going to just move the 1/2 out. I really don't need to really care about it. I'm going to do e to the 1 over r divided by 1 over r. I again use a little L'Hopital's rule. Again. Same thing on the top again. I would still get a negative 1 over r squared e to the 1 over r. However, this time on the bottom, I'm going to get a negative 1 over r squared as well. I'm going to get that. And so here, I'm going to cancel out these guys. And I'm officially going to get a 1/2 times the limit. You guys can't see that anymore. Sorry. Here we go. 1/2 limit as r approaches 0 from the right of e to the 1 over r. And that's where I am, right? So if I do this now, regardless as I go to 0 here, this is going to have to go to infinity. Because as I go from 0 here, it's going to be just going to infinity here. There's nothing else. So regardless of direction, we're going to actually be able to, you know, calculate this limit. This limit here is in infinity. So the limit itself does exist. It's always going to go to infinity regardless as I go up to it here. And so as I found here, all the directions as I approach it will always go to infinity, and therefore the limit of this function as I approach the origin will be infinite. And that's kind of my problem for that. So kind of backing up here, this is you know, L'Hopital's rule over and over again, kind of twice, not over and over again, but just twice. And the reason why we did it, kind of just hearkening back, is we saw here that I have this x squared plus y squared. I have this x squared plus y squared, both in these places, and I don't see an obvious way to show that the limit doesn't exist, or maybe an obvious way to show that it's, you know, it works. What I do is I just replace x with r cosine theta, replace y with r sine of theta. And the important thing to remember here is once you get to this point, you know, this limit right here, once you've changed it, it has to be from 0, from the positive side. As well, this has to work for all theta. You know, this has to work for all theta. So if you can find a theta direction where this limit, it makes a difference, right? That means that I'm coming in from a different angle. I'm coming in from a different angle, and I'm getting a different value. So this has to hold for all theta. If it does not hold for all theta, if you can find a theta value such that, you know, this gives me a different limit, then we know that the limit doesn't exist. If it holds for all theta, then that limit exists and is that value. Here, just to make sure it holds for all theta. If it doesn't hold for all theta, we have a problem. Yeah, that's kind of how you would do this problem. Does that make sense?
Yeah, that's good.
Okay. Okay. Any questions about this guy? All right, what other questions do you guys have? What are things going to talk about? Are you all staying safe? Are you doing okay? I know it's kind of a weird situation at the moment. I hope you're all staying safe and all that. If you have any other questions, let me know. Trying to see if anybody else has any posted anything here. Yeah. Trying to think about other things that you might want to try to think about. So let's kind of review, you know, I guess kind of going forward, what is in each section here. So 14.1, things you really need to know are calculating the domain of a function, a multivariable function. You know, being able to draw level curves is an important one. If I give you a level curve, you know, being able to draw that. That's really basically that guy, at least for that first part. You want to understand what level curves are just in general.
I have a question.
Yes.
Could we do an example where we draw a level curve?
Sure. Yeah. Do you have one, or do you mind if I just come up with one?
You can come up with one.
Okay. Shortly. Let me come up with that. So, I think I actually had one on this. I think I had something like this. Yeah. So, let's consider this function here. F of fxy is equal to the square root of x squared xy minus 1 here. So if I have f of xy is equal to the square root of xy minus 1. And I realized that there's actually an issue with the answer key on this one because I made a silly mistake on this beforehand. And let's say I want to calculate the level curves and draw the level curves out for k equals 0, 1, and 2. Here. Okay. So if I'm going to go ahead and do this, right? What is the idea of a level curve again? The idea of a level curve is finding all of my values of x and y such that f of xy is equal to k. Right, that's my goal. Is my f of xy equal to k? So in doing this, what I'm going to do is I'm going to kind of assume that there's just a general k here, at least initially. Right, k is equal to the square root of xy minus 1. Let's assume that I just have just a general k. So if I do this, right, if I wanted to solve for maybe x or y, or start to maybe think about what these graphs are going to look like, I'm going to square both sides. I'll get k squared is equal to xy minus 1. I can move this over and I'll get k squared plus 1 is equal to x times y. Okay, that's actually pretty good. So then I can actually just solve this out specifically where y would be equal to k squared plus 1 over x. And what I'm going to do now is just honestly, you know, pick my values of k and start to draw them out and start to see what they would kind of look like and label them properly. So how do I label them properly? So let's first off take k equal to 0. If I take k equal to 0 here, what I can get is I would get y is equal to 1 over x, right? K just being 0 there. So what would that draw? What kind of picture would that draw? Well, 1 over x is actually pretty quick to draw. I know that it's gonna be in two places. It's gonna be here, like that, and it's gonna be down here. And I would like to label this k equal to be 0, something like that. I'll label that k being 0. And I want to be very specific here about, you know, being as careful as possible. You know, I know there's going to be a 0.11 on it. You can do that if you would like. Just at least know that, kind of show that you know what's kind of happening. The next one I'm going to do is k equal to 1. If I do k equal to 1 here, I'm going to get y is equal to 2 over x. Okay, that's the same exact kind of graph, but it's going to be moved up a little bit, right? When x is equal to 1, y is going to be equal to 2. Right, so I'm going to have something like that guy. And similarly, this guy. K equal to 1 there. Something like that. And lastly here, if I have something like, you know, k is equal to 2, I'm going to get y is equal to 5 over x. And so this is, again, if when y is equal to x is equal to 1, y is going to be equal to 5. Right, so it's going to be even farther up here. Something like this. K equal to 2, sorry. K equal to 2, K equal to 2. That's what this kind of shows you. This kind of shows you, and is a way for me to describe, all of the points that are on the same exact height. This kind of what I'm doing here is I'm taking a slice at k equal to 2, and it's going to try and see the imprint of that on there. What you can do it a couple different ways if you would like. You could do it with a general k, as I've kind of done here, and then just plug in k values for that. Sometimes it might get a little bit weird if you do it with a general k, mainly because there might be some special cases for some k's. For instance, let's just assume that I just kind of as a kind of a side note of where this might fail. Let's assume that I had something like let's assume that I had something like f of xy is equal to x times y, right? Something like this. Well, if I did a k equal to 0, if I wanted to find my level curves for this surface, and I did k equal to 0, right? If I just did a general k, I would get this is k is equal to xy. You might go, oh, okay, xy is equal to, k over x. Okay, but if I did k equal to 0, right, if I plug this in, I would get y is equal to 0. So you might say to yourself, and kind of like, okay, well, that's just, the x-axis. But you have to be very careful. Now, why is that? Well, if I take a look up here, if I had plugged in k equal to 0 here, right, what does that say? Right, that says there that either x can be 0 or y can be 0. And so you should have two kind of parts of a level curve. You should have both on the x and the y. So it's actually really important, kind of a subtle difference. So you should always be careful to check, all right, am I missing anything? Am I missing anything by dividing out, right? Because dividing out could be a very bad thing. So just making sure that, you can leave it as general as possible, as general k, but make sure that if you plug in something and things start to go away or might seem a little wonky, go back and just plug in that value initially and see what happens. Maybe in this case, right, I missed a full line because I did that. So it's just an important little facet there to make sure that, general Ks are good, but some weird cases might admit something very different. That's kind of how you do level curves, making sure that you label things very carefully. If you don't have to use different colors, you shouldn't use different colors, but at least making sure that you have, k equal to 2, k equal to 3, make sure that it's labeled correctly. So we at least know, kind of going from that. And that's kind of all the work that you show for that. Does that answer your question?
Yeah, so like basically what we should do is kind of replace f of x of y with k and then solve for y, and so it's easier to be able to draw our graphs up.
Yeah, sometimes though it's not really possible to solve for y. So you just kind of have to go just as a general one. So for instance, if you had something like x squared plus y squared, you just have circles.
Okay.
Right, something like that. It's okay if it's implicitly defined. But sometimes you just either solve for x equals something or y equals something, one of the two. If you get one of the two, you can draw that out pretty quickly.
Right,
sometimes other than that, just kind of, you should just see what it looks like, right? Something maybe like a hyperbola, maybe some other concept.
Okay, cool, thank you.
No problem. Keep forgetting to drink my water. Okay, so that's at least that aspect. I realized that there's a silly mistake on that answer key, so I'll fix that because this should be an answer instead of the one I wrote. So so now kind of going through. So that's kind of right. Make sure you know how to calculate the domain and draw the domain of a multivariable function. In the 14.2, it's all limits. So make sure you know how to at least compute one limit thing. Know how to show that a limit doesn't exist. Right, that's really important. Making sure that you know some just basic general tricks. Something like multiplying by the conjugate in the top and bottom. Converting to polar coordinates is a good one. Canceling things, factoring is also a really important one. Can you factor? Stuff like that. And then 14.3 starts to get into partial derivatives. Being able to understand why partial derivatives, how to calculate a partial derivative, how to interpret a partial derivative. Also in 14.3, near the end of that section, we kind of discuss, so 14.3, yeah. So there's also like computing mixed partial derivatives, right? So there's Chloros Theorem. Chloros Theorem says that fxy is equal to fyx, if and only if f is continuous. and we're on a continuous unrighted disk. So make sure that we're continuous there. We can flip the order of differentiation, not integration. Yeah. So you can flip the order of integration there, at least in any way you want. So make sure you know how to compute mixed partial derivatives. Make sure that maybe there's a simpler way to go about it if everything's consistent. If everything's continuous there. 14.4, making sure you know how to compute a linearization. Right. The way I like to consider linearizations, I know that's in tangent planes, at least in that section, is I like to kind of relate it back in some way to how to do a tangent line. And why would I do that? Right? Why would I do that? Well, just kind of remind yourself, if I have, some function like this that you cannot see, some function like this. I have a point right here, and I want to compute my tangent line. Maybe this is when x is equal to a. Let's do something very general. Right? I know that here, right, the slope, I know actually something really interesting, right? I know that the slope here, using point slope form, I can actually know that the slope here is equal to y minus y0 over x minus x0. Maybe this is a point x0, y0 instead. And a general y. The slope of that line is something like y minus y0 over x minus x0. And point slope form can actually be written pretty nicely if I cross multiply here. I get y minus y0 equals m times x minus x0. Moving over the y0, I would get y is equal to y0 plus m x minus x0. Usually this m here can be exchanged. And sometimes even the y0 can be exchanged if I know what an f is. This could be f at x0, right? F at x0. This m here is the derivative at x0, right? Times x minus x0. Now, I have this tangent line, which is, again, a linear approximation. This is what I get from my linear approximation around this point, right? It's a good approximation around here. As I get closer, farther and farther away, the line does not approximate the function very well. Right, so if I have a linear approximation there. Now, if I have a linear approximation here, and it kind of looks like if I just want to extend it, if I have one more variable, wouldn't it be nice if I could just extend this again with y? And I can. I just have to be very careful, right? Because I know that derivatives are not really explicitly defined. I have to be very careful which direction I'm taking a derivative. But just in general, if I have a function of f of xy, right, it looks very similar, right? L of xy here is going to be equal to the function value at my point x0, y0, the derivative of x at x0, y0 times x minus x0 plus the derivative at y. Something like that. It's just a very natural extension of point slope form. In that case, it's just a very natural extension. And because of that, this gives rise to the idea of linear approximations. In the same way that I do a linear approximation of a line, it's the same thing with a linear approximation of a plane. I'm just now going in the x and y directions, which now gets a plane. It's kind of all you do. So it's not really about a memorization. It's kind of just saying, okay, how do I do a tangent line? Extend it one more. It's kind of nice. Differentials, I don't know why they would, I don't think they would really ask that a ton at all. I've never seen actually a problem about differentials. It's very kind of tough to test on that anyway. So I'm going to kind of ignore that for the time being. But being able to write a tangent line, like tangent plane, right? This is a tangent plane, right? If this is z is equal to a function of x, y, you can do some linear approximations to that. 14.5 is all about the chain rule. Make sure you know how to do the chain rule. Implicit function theorem on top of that too. Kind of going from there. And then 14.6, it's actually a pretty long section, 14.6. So right, we have the idea of directional derivatives, knowing how to compute directional derivatives, knowing how to compute directional derivatives with the idea of the gradient in it, making sure that you know how to compute, the unit vector in the direction in many different aspects, right? Making sure you divide by the magnitude, make sure you go in the same direction, right? Make sure you maybe use cosine theta, sine theta if I have a theta direction. Similarly, we can then say specifically that what does the gradient mean? The gradient is the direction of steepest descent, and the negative direction, and the direction of steepest descent is the exact opposite direction of the gradient. It's kind of nice, and you can show that very quickly. If anybody wants me to show that, I can. And the magnitude of the gradient is actually the rate of change, is the maximum rate of change of my function at a point specifically. We also found a different way to write the equation of a tangent plane. In this section, if I have a function of f of x, y, z, something like that, if I have a function of f of x, y, z, right? This is a one way to write the tangent plane, but let's say z is implicitly defined, right? As I've said before, something like f of x, y, z is equal to 0, something like that. We know that the normal vector for our plane would then be the gradient at our specific point that we're worried about. And in doing that, we can find some really important things too. And that gives us a rise to the idea, again, that gradients are always normal vectors or orthogonal to level curves or surfaces, however you want to think about it. They're always orthogonal to level surfaces. They're always normal to level surfaces or level curves. Think about it. So you'll be able to draw that out. Visually, right, we also tackled here, being able to visually see if the directional derivative or a partial derivative is positive or negative or 0, depending on looking at contour plots too. So we've already tackled that. Thinking about more general, problems like that, I mean, there's not a ton of other geometries other than maybe looking at a graph and saying, is this fx, fy? Right? We kind of discussed kind of how that kind of arises, right? Kind of thinking that if I take a point and I go in the x direction or I go in the y direction, find a point that's very different, right, in the x direction and the y direction, kind of moving, how fast am I changing my height? If one's really fast slope and one's maybe not very fast at all, you can see that very, very quickly over in the graph of fx and fy. So that's a really important way to kind of go about that. Yeah, and that's basically it. Basically it, I say. Basically it. We're not doing 14.7 and 14.8 actually until the end of the semester. We actually tackle maxims, mins at the end of the semester because that's actually a really weird, interesting way of coming back. Yeah, I think that's it, at least from the time being. I mean, I can answer any other questions you have. I will stick around for another 30 minutes. Does anybody else have any other questions that I can answer? Anything you want me to answer?
Could we do a problem that involves like finding the parametric equations of a tangent line?
So I don't think you would really be asked that on this kind of thing. Parametric equations for a tangent line to what specifically? Like a surface?
I think it would be to a surface. I'm just looking at the mini exam, like the bullet points.
Yeah.
And it says finding the parametric equations of a tangent line arising in the above geometric interpretation, and that's like it says interpreting a partial derivative geometrically.
Yes. I see what you're saying. I'm sorry.
Mm-hmm.
I know. I see what you're getting at. Yeah. So I guess. How do I want to go about that?
This might be hard to do because you kind of have to draw it, but.
No, I actually don't have to draw it. We can actually do it all by hand, which is nice. We're doing this kind of thing by hand, so we can definitely do it by hand. That's not a problem. Well, let's at least. I guess the big thing here, I guess, to realize, and this extending this geometric interpretation of a directional derivative, is really the following. I'm going to attempt to draw this as best as I can. So please bear with me if my drawing is not the best. I'm going to try my best here. I don't know why it's really funny. It kind of is mimicking, it seems like this whiteboard's mimicking like my marker is dying, which shouldn't really happen on a whiteboard online. I don't know why. But let's kind of tackle something just very basically here. Let's see. Let's assume I have this surface. Let's assume this is some z equals f of x, y. Okay, and I have some z equals f of x, y, and I want to find the derivative with respect to x, right? What does this actually mean at a point? So let's make a point here. Let's make a point. I'm actually not going to use black. We're going to make this very apparent. Maybe something like this here. Okay, so this is my point here. I'm going to name this point this point x0, y0. And my goal is to start to think about what the idea of the derivative with respect to x is at this point. So the idea again here is, let's assume that this is, I don't know, some point x0, y0. I'm gonna name this actually point AB, a little bit easier for me to think about. So this is A here, and this is B here. And I want to think about the idea of fx's specifically. And I want to find, how about this? And this is what I'm going to try to do. I'm going to try to find an equation for the parametric equations for the tangent line going in the x direction. That's kind of my goal here overall. And that's what the idea of fx actually is. And now why is that? Well, again, when I take the derivative with respect to x, what I do here is I take the plane, again, I assume that y is a constant, right? So I assume that y is a constant. So y equal to b is a plane in the y direction. In this direction here. It's kind of this plane here. And something like this guy. Some plane like that. And what's interesting is the intersection of this plane, something like this. I hope you guys can see that. That would be like the intersection if I took this plane and I kind of slid it in to this. What I'm doing there is I'm taking this plane as a constant, right? Y is a constant, and that's the plane. I'm just kind of sliding this in. And what I'm doing is I'm finding the intersection between the constant y equal to b plane and the function f of xy. At this point right here, I now have this curve, right? I can find the tangent line to that curve in that direction. Something like that guy. I hope everybody agrees with that. If anybody has any questions what I'm doing right there, let me know. What I'm doing here is, again, I'm taking my plane y equal to b. I'm sliding that in. I'm finding the intersection of the surface and y equal to b. I'm finding that intersection. And then what I'm doing is I'm finding on that intersection curve the tangent line at that point in that direction of that here. And it would be that green line. And so now, if I want to think about here, if I want to think about specifically what the slope of that line is, the slope of that line is fx. Now, what does fx actually mean, right? Well, again, if I was to write the equation of a line here in vector form, I have r of t is equal to r0 plus v times t, right? That's what I would need. R0 is a point, and v is a direction vector, right? This point here is pretty quick for me to solve, right? Because if I have AB, this is just f at AB. I know that's a point on my curve, right? If I have a point AB, I put in for f of x, y, A and B, and that's my point. So my R0 here is actually really nice. It's always going to be A, B, f at AB. Now the direction vector v really changes depending on it. Now, think about what the direction here that I'm going in, and what the idea again of a partial derivative is. A partial derivative with respect to x is I am going 1 in the x direction, and I'm not changing my y at all, right? I'm not changing y whatsoever, so I'm not moving at all in the y direction. And then how fast do I move in the z direction? Well, that literally is the derivative with respect to x. There. And so in this case, with the derivative with respect to x, this literally is my direction vector. And putting all of this in, I can actually get the equations for a tangent line. Right? I'll get r of t is equal to a, b, f of a, b, plus t times 1, 0, fx at a, b. And going through this whole thing, you would start to come up with your parametric equations, right? Your x would be a plus t, your y would just be b because it's not moving. That would make sense, right? It shouldn't be affected by time, I'm not moving. And similarly, your z would be affected by the derivative with respect to x over time. And so these would be the ideas of parametric equations. You could also think about in the same exact way, let's assume then maybe what I did is I wanted to find f sub y. I want to find the tangent line in the y direction. In the same exact way, I take now my plane with y x equal to a, right? I again would get some, fun, poorly drawn curve like that. I would again get now a tangent line in this direction. And now, again, my point stays the same. My R0 stays the same. Now, what's my derivative with respect to y here? Well, what's my derivative with respect to y? Well, I'm now, think about this, I'm keeping x constant. So my v here would be something like, okay, I'm not moving x, I'm moving 1 in the y direction, and I move fy in the z direction. And then we can exchange this guy for here, for my value. And we can do this with just a general, which is really crazy. So we can do this with just a general plane. Again, so what does it actually mean? What do I mean by just a general, a direction? Say I pick any direction. I'm gonna move this over here. Say I pick any direction. I pick the direction u. Pretty important that I pick a direction u. It has to be specifically, right? It has to be a unit vector. It's a really important unit vector. Let's say I pick a unit vector and I'm gonna be going in, I'll name it u sub x. That's a horrible name for that. Sorry. I'm not gonna use u sub x and u sub y. That seems too derivative. Maybe something like u sub 0, yeah. I can't even do that. I'm just gonna name 2 things. Let's go C and D. Can't do that. I'm gonna go in some direction, right? So think about what this means. This means here that I'm going in some direction, maybe is in this direction. If you look at what I'm drawing in the thing here, maybe I'm going in this direction, right? Maybe that's CD. What I'll again do here is I would again, this sounds silly, I would take the plane going in that direction, find the slope of that line going again in that direction, find the intersection of that plane now, go in that direction here, again, and find the derivative. Now, how do I find the derivative slope of that? That is the derivative of f with respect to u. That literally is the directional derivative at AB. That literally is the directional derivative at AB. And so what does that actually say? Right, what does that actually say? Well, if I want to find my direction vector of my slope here, where is the vector going in my direction? Well, I move, kind of thinking about my direction v now, I move c in the x direction, I move d in the y direction, and then I move the directional derivative in that direction. And what's great is this does not change. The R0 does not change. I'm still staying at that point. I'm not changing. But I can come up with any tangent line I would like just by this method, right? I'm going in a little bit in the c direction, a little bit in the d direction, a little bit in the x, a little bit in the y. How much am I moving in the z? That gives me the direction. And from here, I can come back and come up with specifically the equation for the tangent line. Most of the time, we're going to be using just fx and fy, right? So I'm moving 1 in the x direction, 0 in the y direction, and how much in the z direction? Fx. Maybe in the y direction, I'm moving 0 in the x, 1 in the y, how much moving in the y? And this could then get me my equations for my tangent lines, specifically. So I hope this picture starts to make more sense now. At least maybe how you want to start to do these things. And maybe, coming up with the ideas of tangent lines. All is about intersections of planes and coming up with that. R0 stays the same, the direction vector changes, depending on the derivative. And it comes from the derivative, as it should, as it absolutely should. It just depends on which kind of derivative you're taking. Any questions about that? Okay, what other questions can I have? I have about 15 more minutes, so does anybody have any other questions you want me to tackle?
Yeah, can we go over higher order partial derivatives and something about Chloros Theorem to simplify a computation of higher order partial derivatives?
Yeah, do you have like
I don't have an example. It was just on the
That's okay. It's okay. I mean, I can just come up with one and we can go from there. So let me actually see something. I think there's probably some good ones in Stewart. Well, I mean, I guess the general idea of that, if I just take multiple derivatives, is sometimes, you're absolutely right, sometimes it's a lot easier to take it in one direction rather than the other. And let me see if I can come up with one here. Yeah, something like
I think he has one on the mini exam one, the one DJ gave out. It's number 3.
Yeah, let me actually see. Yeah, you can do that one. Sure. Yeah, you can compute either. So at least let's talk about what Chloros theorem actually is saying, I guess just in general. So if I have a function, I guess Chloros theorem extends to actually as many dimensions as you would like. You can't, infinite dimensions, I'm not going to tackle infinite dimensions. It's kind of a weird thing to say. So I'm not going to really tackle that. But in this case, what I want to think about is if I have a function f of x, y, which in this case is e to the x squared plus y times arctan of xy. My goal is to evaluate fxy at 1, 0. I want to remind myself what Chloros theorem says. Chloros theorem actually says if f is continuous around a disk, around a certain point, that I know, if f is continuous around a point, that I know that I can take the order of differentiation however I would like. I can take it with respect to y first and then x. I can take it with respect to x and then y. It does not matter which one you take first. If you want to rip off the Band-Aid, which I sometimes like to do, rip off the Band-Aid and take the worst one first, that's cool. Sometimes it really doesn't, it can't help you either way. Sometimes it can really help. For instance, if I did something like, if I have something like f of xy is equal to, you know, I don't know, something pretty nasty, you know, x plus, you know, arctan of like y squared plus like the square root of y or something like that. I need to calculate f yx. I guess I'm not taking that derivative with respect to y first in any sense of the word, right? I would not do that at all, right? I can say that, okay, this is f of xy, so just take fx first, and that's 1, and then fxy would then be 0. Right, so this is a really simple example, really bad example. But you can at least see that changing the order really does matter. It can really affect it. So I'm going to take this guy, and I'm going to take this with respect to x first and with respect to y. Honestly, I don't see that there's going to be a really better way because kind of looking at this, right? If I look at this, I have a function of x and y multiplied by another function of x and y. I'm going to have to use, you know, the product rule here regardless. So I might as well just, you know, just go for it. And I can't really do anything else. So what I'm going to do first here, I'm going to go with respect to x first. I'm just going to do the worst one, I think, out of the way. Because I think the x squared is a little bit worse. And we'll have to carry something through. So I'm just going to do that first here. So I'm going to take the derivative with respect to x first. Doing this, I'm going to do product rule. So e to the x squared y, the derivative of that is going to be 2x times e to the x squared plus y. Again, by arctan of xy, something like this. Plus, well, what's the derivative of arctan? The derivative of arctan is 1 over 1 plus whatever's inside. So I have e to the x squared plus y divided by 1 plus xy squared. But then I have to multiply it by the derivative of xy with respect to x, which is y. Which is y. So I would get that this is multiplied by y here. And we get this very fun, very nice equation. I'm going to factor out probably the e to the x squared plus y because I don't want to deal with that if I can. So e to the x squared plus y, and then I would get a 2x arctan of xy plus 1 y over 1 plus xy squared. I'll get something like that here. Okay, cool. Now what I have to do is I have to take this derivative now with respect to y. Taking this derivative with respect to y, I'm going to have to use the product rule again. The first one's pretty easy. It doesn't change, right? Because this derivative of this guy with respect to y does not change. So I'm going to just, there'll be e to the x squared plus y, because I don't have any like chain rule kind of stuff to worry about. So I have e to the x squared plus y. And then this whole thing again, arctan of xy plus y over 1 plus xy squared. And now I'm going to take the derivative of this inside here. Let's got this inside. So in doing this, I don't have to use product rule for this first one. The derivative of arctan again is 1 over 1 plus x squared, xy squared, multiplied by the derivative of that with respect to y, which is going to be x. Okay. This guy over here, I'm going to have to use quotient rule. It's not really any way around that. I think I'm going to have to use quotient rule here. So using quotient rule, it's f prime g minus g prime f. So f prime, the derivative of the top, high d low. No, sorry, yeah, high d low. No, sorry, yeah. So if I have f over g is equal to f prime g minus g prime f over g squared. So I'm going to take the derivative of the top. It's just going to be 1 plus xy squared minus the derivative of the bottom here, which is going to be the derivative with respect to y specifically, is going to be, we'll have y out. The derivative of that is going to be 2 times xy, chain rule, derivative with respect to y is x. Divide that by 1 plus xy squared, squared. Cool. So now we've got this whole thing. And that's my derivative. And now I'm not simplifying this at all. I'm just going to calculate fxy at 1, at 0, 1. I think it's 1, 0. Yep. Because I'm not touching that with a 10-foot pole. So I'm simplifying this. The first thing I would notice is that e is just going to stay outside. Or that e, it's going to be e to the first power. I'm going to get 2 times x, which is going to be 2 times arctan of 0, plus this whole thing is going to be 0. That's nice. Again, I'm going to have e again here. And I'm going to get, in this case, ooh, let me just move this over a little bit. That's all on the top. This guy here is going to be just 2 over 1. That's fun. Here. And then this top one over on this other side is going to be just 1 minus 0 divided by 1 again. And I think that's it here. Yeah, so arctan of 0, right? Arctan of 0, well, when is tangent 0? That's when, that's at 0, here specifically. Right? Yeah, that's at 0. So with that in mind, arctan of 0 is 0. Yeah, arctan of 0 is 0. So this entire thing goes away. And then over here, I'm left with a 2 plus 1, so this is going to just be 3e. And that is my answer. Here, I'm zooming out. Look at that. I think DJ's thing is wrong at the moment, I think. Am I wrong with that? Yeah.
I think it should be 2 over 2 because it's, I guess, what is this, the third term? It would be 1 plus 1 under the 2. So
oh, but that's 1 times 0, though.
But isn't there a 1 also in the denominator? So it's 1 plus, oh, I see what you're saying.
Yeah.
Okay, no, you're right.
Yeah.
Yeah.
I think DJ wrote there x squared times y, which I think is the issue there. So
okay, yeah.
He's going to get something a little bit different. So it should be 3e. That's at least what I've been getting.
Yeah.
I think that makes
good.
sense. Yeah. So in conclusion, out of all this, how do you go about it? Honestly, there's not really an easy way. Sometimes you just gotta kind of suck it up and go for it if you don't have Mathematica with you. But the goal, again, is to remind yourself when you're taking derivative with respect to x or with respect to y, you're leaving one of the other as constant. And you're just going to keep just doing it over and over again in that case. Does that answer your question? I forget who asked that. I'm sorry. I've been just too in the weeds here with Arctan.
Yeah, that answers my questions. I'm just curious, it's not going to be, just because this would take, if our mini exam is going to be done like 30 to 50 minutes, it said, this would be way too complicated to do during that time.
Yeah, I would agree.
So I guess we should probably, this is just, maybe he put these on here so that we'd be prepared for the work.
Yes, 100%.
We shouldn't expect it
to be prepared.
Bad.
Clearly. We have actually just been told, I think it's going to be 40 minutes.
Okay.
Your mini exam, just as officially. I think I actually just got an email from DJ. Yeah, I literally just got an email from DJ about that. It's just gonna be 40 minutes.
Okay.
Yeah, I don't. I will not see the quiz until you guys do. So I will actually. Yeah, I do not think it will be this complicated. But I think his point here was to show you that just to make the harder the questions, the more prepared you'll actually be.
Yeah, that makes sense. Okay, thank you.
Yeah, no problem. Yeah, so I have a little bit more time. Does anybody have just a general questions that I could answer? I could talk about how I was just studying. I could talk about any other concepts you want me to kind of discuss.
How would you suggest studying?
So first off, always math is a participation sport. So make sure you're doing problems. I think one of the pitfalls that I've seen in the past, so just so you guys know my background, because I find this really important. I was originally a math education teacher, math education major. And then I found out I liked math too much. So I love teaching. So I've kind of seen some really interesting, especially when I've been tutoring and teaching over the last several years, even when I taught in high school. And it seems like a lot of times when students are studying, they have their notes with them and they use them as a crutch almost. They have it and they kind of involuntarily look at it when they see a problem. And that gives you a false sense of security, I think, a lot of times, because you're like, oh, I know how to do that. And there's actually, I think there's an episode of It's Always Sunny in Philadelphia that has that exact same scene in it. And you're like, oh, I know how to, I could have done that without my notes. I could do that. Like, see, watching me do this is really good. It's really good to do that, but you must do the problems yourselves. Go ahead and struggle a while. It's really important to struggle, because the more you struggle with it, the more ways you find how your brain works. How does your brain think about these problems more? I will try to explain how I come up with my problems, but it's really important for you to, explain your own process and go about your own way. Another way I would suggest doing it is, and this is a process that I would do all the time when I was studying, is pick any topic. Literally pick any topic. Let's say, tangent planes. Just go ahead for 15 minutes. Write as much as you know about tangent planes, how to calculate them, how they think about them geometrically, why the formulas work the way they do. You can even come up with a problem yourself, just randomly. You can come up with a problem yourself and just kind of do it out. After you're done, go back into your notes and see what you forgot, what you remembered, what mistakes you made. And these things now, the things you've forgotten and maybe made mistakes on, will now be heightened, because you'll know the mistakes you made, and you'll know that they're on the front of your mind now, so that when you see problems like that, you'll be going forward. It'll be better. That's at least how I really enjoy studying. I take problems, not looking at my notes a lot. I also do look at my notes very frequently, though. I mean, it's really important for you to go through, make sure you know definitions, make sure you know what all the notation looks like. There's very new notation here. And if you don't know what the notation is, you don't know what question you're getting asked. That's a really important factor to go through it. Make sure you know what everything is actually asking for. Are you asking for a value? Are you asking for a plane? Am I asking for a function? What am I actually asking for? Those are things you should always make sure you're doing. So I would always suggest, go through your web assignment, go to the back there, make sure you do all these practice quizzes and all that. Make sure it's okay if you do a problem yourself in a different way, if you get the same answer, if it's mathematically correct. make sure that, you know, either post on Piazza or something like that. Say like, hey, does anyone mind just checking my answer here? It's a little bit different of a method, because there are different methods here to go about them. Yeah, that's at least how I would suggest, you know, studying going forward. It's really important to just kind of keep doing the applications and keep doing problems. You know, you can watch me do problems, you can watch other students do problems all day, and it's a really good thing to do. I love studying with each other, but you gotta do it there. Yeah, that's how I would suggest studying. Okay, does anybody else have any other questions? It is 3:02. Okay, so without that, I'm gonna do this tomorrow too. I'm gonna post this whole video on the YouTube page, just as a private YouTube video, so you can so you guys can all watch it. Let me know if you have any other questions, and I'm gonna have this tomorrow. Thank you all for coming. I hope you have, you know, if you're celebrating anything today or this last week, happy Easter, happy Passover, and I hope you're staying safe. And yeah, thank you for coming. I appreciate it. Oh, where is there's my share screen. There you go. Oh, it's Tuesday. Oh, somebody asked that. Tuesday.